Chapter 6, Section 10, Mechanism Protein Synthesis. Okay, 3 steps you got to keep in mind. Initiation, elongation, termination. Get it started, keep it going, stop it. All right, we're going to be looking at the players, messenger RNA, tRNA, ribosomes. There's going to be, other multiple proteins that are coming into play. And then we're going to need some GTP for energy to get this bad boy going. Ribosomes, okay? Ribosomes, okay? RNA is predominant. Some proteins, but RNA is the predominant. It's large complexes, multiple RNAs, multiple small proteins. There are going to be thousands of them in every cell. The more protein synthesis a cell does for its metabolism, the more ribosomes are going to be there. 2 subunits, large and small, okay? 30 and 50 in prokaryotes. 30, 50, small, large. They come together to form the 70S. And no, it does not add up. Okay, this is known as Fedberg units. Okay, this is when they put it into, they'll isolate the ribosomes and all the parts, and they'll centrifuge it in a gradient. And how far down in the gradient it moves is what units they give it. So small subunit moved down to where they said corresponds to 30. Large one moved down to where they said it corresponds to 50. The complete 2 of them together only moved to the 70, which is why you go and look. 30 contains 16 and the S and some 21 proteins. 50 contains 5, 23, and a whole bunch more proteins. You're also going to see translation factors, some proteins that are going to bind to the messenger RNA, they're going to interact with and help start things off and help keep things going. 50 and the 30. Mil total make a 70S. Small subunit, large subunit. You're going to have what's called an initiation complex. All right. The initiation complex, the 30S, the messenger RNA, the FMET tRNA, and then a bunch of what they call initiation factors, IF1, 2, 3. Okay? All of these come together at the 5' end of the messenger RNA. Once all of those are together and stable, then you get the large subunit come into play and you have the complete thing. So how does this work? FMET is going to go to the AUG that's closest to the 5' end. Small subunit's going to start at the 5' end, move down till it hits where the tRNA is. The initiation factors are also going to interact down at the 5' end. All of these together brings in the large subunit. Once the small and the large subunit are there, you have the first amino acid in that tRNA in the P site. Means the second codon is now open. tRNA with the correct anticodon is going to come in. There you go. You now have 2 peptides because the large subunit is now going to join the 2 peptides together. The ribosome will translocate. Now it moves so that the tRNA from the second codon is now in the P site. A site's open. That first initiation tRNA is kicked out of the E, and it just keeps going. Is that everything on how to get it started, how to get it going? No, that's more than enough that you need to know. The mRNA threads through the ribosome between the large and the small subunit. A, P, E sites. A is the acceptor. This is where the tRNA comes in. And remember, it's not going to always be the correct tRNA. It's just random which tRNAs are coming in. They come in, they pop out. Come in, pop out, unless there's a codon-anticodon interaction. Then it stays and it's stable. Large subunit does its job. The loading is assisted by what is known as EF2. EF2. EF2 is an elongation factor. It's going to aid in the cutting of the growing polypeptide from the tRNA in the P site, transferring it over to the tRNA in the A site that's already bringing in the next amino acid. You could just sit there and watch it. It just keeps doing this over and over and over. What we find is interesting is we draw it in textbooks. We discuss it as one messenger RNA, one ribosome, when in reality, it's one messenger RNA and as many ribosomes as can hop on and march down it, making the polypeptide. As many can hop on and march down it until the messenger RNA gets chewed up. Because remember, starting at the 3' end, chop, 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 chop. So you can end up with dozens of ribosomes marching down, codon by codon, making dozens and dozens of copies of that polypeptide that's called for by that messenger RNA. When it hits the stop codon, there's going to be a release factor. Okay? This release factor is going to interact with one of those stop codons in the A site. It's going to cause everything to pause. Pauses long enough, ribosome just disassociates, falls off, cuts, releases the now finished polypeptide. You can see here, as these are marching down, this could be, ribosome 1, 2, or 3, 4, they're all marching down. As they're marching down, the growing polypeptide comes out the top here, and it's already doing all its folds. The alpha helices, the beta sheets. It may not be complete, may need a little help later with some chaperonin proteins or whatnot, but it's getting there. The role of the RNAs, basically it's facilitating. Most of the work is done by the RNA itself. The 16S, which is going to hold the messenger RNA in place, making sure the messenger RNA is positioned in the correct place so that the A and the P sites can interact with it. See that the ribosome RNA is the thing that catalyzes the bonds. Okay, Peptidal Transferase is catalyzed by the 23S ribosomal RNA, which is a component of the large subunit. This is what's cutting the peptide off the tRNA at the P site, transferring it to the tRNA in the A site. And then it's the RNA that's causing the whole ribosome to shift, to translocate, codon by codon by codon. Ribosomes can become trapped if by some reason the stop codon is not there, or some mutation or some slippage, and it just keeps going and going. They call this trapped, because it's just going to keep running off, and it's going to hit the AAA, which the AAA is actually can be a codon, and it's just going to start adding on amino acids after amino acids and after amino acids. Translation. These are small RNAs that free stalled ribosomes. If the ribosome can't stop, because no stop codon, it'll just keep running off the end, or it'll just keep going to a certain point, it just slips and falls off. If it stalls, A stalled ribosome should terminate, fall off. Well, you have some of these small RNAs that can come in and get things started back up. Gets it so that it can start back up and proceed. May not call for the exact amino acids in that little stalled region that should be there. You know, maybe there was a transcription error, spliceosome error, something along the way. But this will keep it going. And there's a good chance, as long as the amino acids, again, are close, or the amino acids that are going to be off, the wrong ones, are in a region that's more structural as opposed to active site, the enzyme could still be functional. Here's what it looks like when you look at a cutaway view. Small, large, A, P, E. Incoming tRNA has a stop codon, has to interact with the codon in the correct way, because this messenger RNA will fold up so that it can now interact there. If it can interact, codon, anticodon, then this tRNA will stay there stably. If they don't interact, because they're not complements, this will be bounced out. If it stays there, now what's going to happen is, since this is a stalled one, notice the weird shape. It's going to insert an alanine right there, causing the whole ribosome to translocate, shift over. Basically, bump starting the ribosome. For those who don't remember, bump starting, if you had an old car that had a stick shift and you couldn't get it started by turning the key, you can just shove it, push the car enough, it will cause the car to start. They call that bump starting. Well, that's what this is, basically. It's bump starting. You are adding on an alanine just randomly, which causes this whole thing to translocate and to start back up and start marching down codon by